discrete mathematics as set of tools which you will be using in all other subjects that you study. Okay, so that's why it is very important. And coming to gate exam also, it is very important. Around 8 to 10 marks of question are asked from discrete mathematics, and many other subjects like TOC and your engineering mathematics and other subjects, they are also based on discrete mathematics. So when we will be learning TOC, at that time, theory of computation, at that time we will be using these concept of discrete mathematics very frequently again and again. So pay attention to this subject, because this is not an isolated subject. Like there are some subjects like compiler design, you do not need those subjects in other that subject in other subjects. So but this subject is actually not just an individual subject, it will be used in other subjects also. So we will start. And again, so first thing that we should ask is, what is discrete mathematics? So if you ask what is discrete mathematics, then I will ask you, what is mathematics? So basically, we cannot define mathematics, but we intuitively we know what is mathematics. Similarly, as we proceed in this course, you will intuitively know what is discrete mathematics. Like when you were child, you were in first class or second class, you were directly taught these kind of things like tables or multiplication, addition, these kind of things. At that time, you did not ask what is mathematics, and no one told you what is mathematics. But slowly, as as you grew up and so you intuitively understood what is mathematics. No one was there to tell you the precise definition of mathematics. Similarly, we will see some like we cannot precisely define discrete mathematics, but there is some way, like we can cover the major aspect of discrete mathematics by that definition. But those definition we will see by the end of this course, because as we proceed, by the end of this course, you will develop this intuition, this intuitive understanding of what discrete mathematics is. So at that time, I won't even need to tell you what is discrete mathematics. So that's why we will proceed further. And then at the end, we will we will just see what we have studied, and we will try to come up with some definition of discrete mathematics. So let's start. In this discrete mathematics, what are the things that we will see? So in this course, we will divide this course in 5 modules. The first module is mathematical logic. The second module is combinatorics. In combinatorics, we will be studying how to count and other things, so these counting problems. And now in set theory, we will study about sets and relations, functions, poset, lattices, and other things. In group theory, and there is graph theory. So we have divided this course in 5 modules, and we will cover one module after module by module. We will cover this course. So let's start with the first module, that is logic or mathematical logic. Now, in this mathematical what is first we can think like what is mathematical logic or what is logic. So logic is actually a way, it gives you some tools, it gives you some methods to write any mathematical theorem in a precise manner. Because when we speak in general, like when we are speaking English, there is so much ambiguity. But we just sometimes we just feel what the other person is saying, and we just understand what they are saying. But in mathematics, we cannot do this. In computer science, we cannot do this. We have to tell the machine, we have to tell the artificial intelligence, these tools, what we precisely mean. So we have to come up with some precise notations for our mathematical theorems. So that's why in this mathematical logic, this branch of discrete mathematics, this is this we are studying. So again, as we move on, as we as we see some tools, as we see some examples and all, it will be clear what is mathematical logic and everything. In this course, this mathematical logic, again we will divide it into two sub modules. The first is propositional logic, and the other is first order logic or predicate calculus. So this first order logic that let me write. So this first order logic, this is very important, and wait a second. Mm. So this wait a second. Right. Yeah. So let's see first this propositional logic. So this propositional logic is actually subset of this first order logic that we will study later. So first we will see what is this propositional logic. In this is a very easy topic, and actually if you when we study this propositional logic, there is something there is a subject in you have a subject called digital logic, right? So in digital logic you have a chapter named Boolean algebra. So this propositional logic is actually similar, or you can say analogous to that chapter Boolean algebra. So if you already know this Boolean algebra, then this chapter, this propositional logic chapter, will be very easy for you. And even if you do not know Boolean algebra, then also no problem, because anyway we are going to study this chapter in a very detailed manner. So once you will understand this chapter, automatically in when you will move on, when you will move to the digital logic subject, and in that digital logic subject, when you will study this Boolean algebra, so understanding that Boolean algebra will become very easy for you, and it will save time. So let's start with propositional logic. In today's class, whatever we will study, that will come under propositional logic. And as I said, as I mentioned earlier, after the at the end of this propositional logic, we will precisely define what is propositional logic. So don't worry about the definition of propositional logic this chapter. Right now, at the end, we will precisely define what is propositional logic, and it will become easier for you to understand. So even in most of the standard textbooks, they do like this. So they first teach everything about this propositional logic, and at the end they define what is actually they mean by this propositional logic. So let's start this subchapter, propositional logic. So in propositional logic, again, we have divided it into some topics. These are some topics that we will study. We will see them one by one. Okay. Now, the first thing that we will start with is proposition. So this is a basic building block of logic, this mathematical logic, whether it is propositional logic or whether it is first order logic. We don't in both of them, this proposition is a basic building block. So we will first study what is a proposition. What is a proposition? So a proposition is nothing but a declarative sentence, a sentence which declares a fact. For example, I can say my name is Deepak. Now that is a fact, right? So we can assign this statement that I have, this sentence that I have spoken, like my name is Deepak. This sentence, we can assign either true or false to this sentence. Hence, we say that this sentence is a proposition. For example, if I say my name is Ram, then we can assign false to that. So still that sentence is still a proposition. So basically, proposition is a declarative sentence which declares a fact. Okay. That is either true or false. Now we can either assign true to that sentence, or we can assign false to that sentence, but not both. We will see some sentences which are both true and false, and we will also see some sentences which are neither true nor false. So what is a proposition? Proposition is a sentence, as a declarative sentence, which is either true or false. For example, you can check these 5 examples, and think whether they are proposition or not. Like the first example, Toronto is the capital of Canada. So now this is a declarative sentence. This is declaring that Toronto, some city, is a capital of Canada. We do not care whether we know about this or not, because like I don't know whether Toronto is capital of Canada or not, but I do not care. I know that this is a declarative sentence, and uh, if I knew whether if I were in Canada, or maybe if I was good in GK, then I would know whether this sentence is true or false. But there is one guarantee, that it is either true or it is false. So we can say that this is a proposition. Now let's come to the next sentence, like this: read this carefully. This is not a declarative sentence, this is a command. Read this carefully. Some parent may be commanding their child. So this is not a fact, this is not a declarative sentence, this is not declaring anything, this is just a command. So this is not a proposition, this is a proposition. Now for example, 1 plus 2 is equal to 3. Now we know that this is true. So again, this is a declarative sentence, because this is declaring that 1 plus 2 is equal to 3. So this is again a proposition. Now coming to this, x plus 1 is equal to 2. So we can you assign true to this sentence? Think about this. Can you assign true to this sentence? This sentence that we are talking about, can you assign true? You cannot assign true, because we do not know what the value of x is. We need some additional information to assign either true or false to this sentence. So basically right now, without knowing about the value of x, I cannot assign true, and also I cannot assign false to this sentence. So we can say that this sentence is neither true nor false. So, okay, but we need some additional information here. For example, if I tell you that x is equal to 3, then you can say that this is false. Okay, so if I give you some additional information about what the value of x is, then this becomes proposition. Right now this is not a proposition. Okay, but this is a declarative sentence, like this is declaring the fact that x plus 1 is equal to 2. But since we do not know the value of x, hence we cannot assign either true or false to this sentence. Hence we can say that we need some additional information to assign either true or false to this sentence. So this is not a proposition. Now coming to this, what time is it? Now this is not a declarative sentence, this is a question. Someone is asking time to some other person. So this is not a declarative sentence, hence this is also not a proposition. Okay, I hope you all understood. This is a very easy thing actually. There is not much. Okay, so we have seen these 5 examples. We will see few more examples. For example, let's take this example, this example, and in this example we have this sentence: drilling for oil caused dinosaurs to become extinct. Okay, so this again is a declarative sentence, because this is declaring the fact that drilling for oil actually was the reason for dinosaurs to become extinct. Now we do not care about it of course it is false, but since it is a declarative sentence and we can assign true or false to this sentence, hence we can say that this is a proposition. Okay, right? So why this is a proposition, I have given a clear explanation here. uh, Two things we need for saying that this sentence is proposition. One thing is that it is a declarative sentence, it is declaring a fact. Okay, and the second thing is that we can see that it is either true or false. Either dinosaurs became extinct because of drilling of drilling for oil, or they did not. Okay, so but we can assign either true or false. In this case I think this is false. So hence we can say that this sentence is proposition. Okay, next again of course it like okay, next let's come to the next. This is lookout. So this lookout, this sentence is not a proposition, because this is not a declarative sentence, this is a command or expression. Okay, so these are very simple things. Let's see, let's quickly move on with these examples. Like third example: how far is it to the next route, next town. Okay, so this is again not a proposition, this is not a declarative sentence, this is just a question. Next fourth. Now, okay, consider this. Ram asked me yesterday how far is it to the next town. Now, is this proposition or not? So this is a proposition because this is declaring the fact that Ram came to me and he asked me yesterday, okay, this question. Now, uh, either Ram asked me this question or Ram did not ask me this question. So I am declaring the fact that Ram asked me this question, and now this sentence either can be true or false. So basically we can say that this is a proposition. Again, next example, x plus 2 is equal to 2x. Again, here we need the value of x, right? Without the value of x, we cannot assign true or false to this sentence. So we can say this is not a proposition. Next example, x plus 2 is equal to 2x when x is equal to 2. So now this is a proposition because we have given the additional information that when x is equal to 2, at that time x plus 2 is equal to 2x. We know that when x is equal to 2, then this is true, right? So we can say that now this becomes a proposition because now we have the information about x, and now we can say we can assign true or false to this. So this sentence is actually we can assign true to this sentence. So this is a proposition. Okay, there is a note that in this fifth sentence, if we are given the information about x, if we are given some value for x, if we assign some value to the variable x, then this sentence also will become proposition. Okay, so these were some examples. Now one last example for this proposition or not. So this sentence, now we have this sentence, this complete thing we have. So think about it, whether it is proposition or not. So let's see. A, this statement is false. So this is a declarative sentence, of course, because this is declaring the fact that statement A is false. Now let's see whether we can assign true to this sentence. Okay, let's assign true. So basically we are assigning true to this sentence. We are saying that A is true. So if we assign true to this sentence, then what will happen? So basically, since A is true, so this thing is true, and this thing is saying that A is false. So as soon as we assign true to A, as soon as we assign true to A, automatically it will make it false, because since we are saying that A is true, then this must be true, and this is saying that A is false. So basically, as soon as we assign true, it will make it false, right? Similarly, if we assign false to A, then what will happen? If we assign false to A, then we are saying that this statement A is false. This statement A is false. But as soon as we say that this statement A is false, then this complete thing is also false. And this thing is saying that this statement A is false. So again, this making is true. So basically, this is saying that A is false. So that makes A true. So you can see that if we assign true, then it becomes false. If we assign false, then it becomes true. So we can say that this this is not a proposition because this is both true and false. Okay, so that was the definition of proposition. We should be able to say either true or false, but not both. Okay, so these were some examples. Okay, in the gate exam, no one will ask you whether some sentence is a proposition or not, but this is a basic building block for this mathematical logic chapter. Hence we have studied this, and hence we have taken 7 examples. Okay, but so this is important thing. Okay, now let's let's move on. So this is the explanation, you can read it out, and after that. Okay, so now So again, this propositional logic, the area that deals with proposition, this is a very vague definition. We will see some precise definition at the end of this propositional logic chapter. Don't worry about that right now. So don't worry about this right now. Now, we have seen some propositions, right? For example, my name is Ram. My name is Deepak. Okay? My name is Deepak. Now, we have seen this, so we know that this is a proposition. Now since this is a long thing to write, so I will write p instead of this. So basically whenever I write p, it will mean that I am talking about this proposition. Okay, so basically like in mathematics we have some numerical variables. For example, x is equal to 5, okay, x is equal to 6. So these are numerical variables. Similarly, in propositional logic we have some propositional variable. Basically they represent the propositions. For example, this proposition, today is Friday, we can represent it, we can represent this using this propositional variable. So basically this propositional variable will okay represent this proposition. So okay, a simple thing, propositional variable. Now the thing is that from now on whatever we study, we will be actually talking about these propositional variable. We will be studying everything in the terms of propositional variable. We will not be we will rarely use some specific propositions. Okay, so basically we will be studying in the terms of propositional variables like p, q. Okay, p might be representing some proposition, q might be representing some other proposition, and so on. Okay, or r. Okay, so this r might be representing some other proposition. So basically these are propositional variables, they represent propositions. Okay, now uh, we know that any proposition either is true or false, right? So for with every proposition we can either assign true or we can assign false. So basically these are called the truth values. Okay, if we have a proposition, if we have a proposition p, so this is a propositional variable, this is representing some proposition. Okay, if that proposition is true, then we will say that a truth value of p is t. Okay, and if that proposition is false, then we will say that truth value of p is false. Okay, so this is what we mean by truth value. So basically every proposition has some truth value. Okay, so that truth value either can be true or it can be false. If the proposition is true, then we will say that the truth value of that proposition is true. Okay, now now since we have seen these propositions, okay, now we will combine two or more propositions and we will make new propositions. Okay, for example, we can take an example like maybe p is some propositional variable. This is representing a proposition, for example, today is Sunday. Okay, so today is Sunday, I'm speaking. So if even if I write like this is like this s is not clearly visible, then also I am speaking. So do not worry about that. Pay attention. Okay. Let's assume q is some other propositional variable, and this is it is raining. It is raining. Okay, so now we have this proposition, we have this proposition, and we can combine these propositions to make new propositions. For example, we can make a new proposition called p and q. Okay, what will be this new proposition? This new proposition will be today is Sunday and it is raining. So basically today is Sunday and it is raining. So this will be a new proposition. So we have combined existing propositions to make new propositions. Such kind of propositions are called compound propositions. So what is a compound proposition? Compound propositions can be formed from existing propositions using some operators. For example, here this and is a operator. Okay, this is a proposition, this is a proposition, and this is a operator, and we have combined these two propositions using this operator, and we have gotten a new proposition p and q. So we will see what are the basic operators. So some of them are standard operators. Okay, that we will be frequently using. Okay, So let's see what are the operators. So now we will study operators, and so let's assume that P and Q are two propositions. So these are actually basically P and Q are two propositional variable, and they are representing some propositions. Okay, so but the this thing actually we will be using interchangeably. Like we can say that P is a proposition, Q is a proposition. Okay, because they are anyway representing propositions. Okay, so now we have some operators in propositional logic, some standard operators we have. So the first operator that we will study is negation operator. Okay, so this negation operator is a unary operator. Basically, unary operator means this actually applies on one proposition. For example, this AND operator, we have applied it on two propositions. We took two proposition P and Q, and we applied this AND operator. Okay, so that was a binary operator. Binary operator means that which is applied on two propositions. So let's see what is negation. So negation is a unary operator. If you have a proposition P, then this proposition P, we can make a new proposition called negation of P. Okay, this is the symbol for that. Okay, this is the symbol for negation operator. So this is negation of P. Now similarly, okay, we will see this negation operator and these all other operators in detail. Okay, so let's see one by one. So first we will see the negation operator. So this is the negation. If we have a proposition P, okay, if we have a proposition P, then negation of P denoted by this is the symbol for negation of P, is the statement that it is not the case that P. So basically this proposition P, if we make a new proposition called negation P, then that statement will be actually it is not the case that P. Okay, so let's see, let's take this example. For example, let's assume that this is P. Let's assume that this proposition, today is Friday, this is P. Let's represent this using this propositional variable P. Now the question is asking, find the negation of this proposition. So what will be the negation of this proposition? Negation of this proposition will be this is the basically this thing is negation of P, right? So this what will be this will be, it is not the case that today is Friday. Okay, we can write like this, it is not the case that, and instead of P we can write this thing. Okay, so we can say that it is not the case that today is Friday. So it will be basically today is not Friday, that's it. Okay, similarly we can take next example. This next example is saying that at least 10 inches of rain fell today in Miami. Okay, so what will be the negation of this? The negation of this statement, this proposition, the negation of this proposition will be, it is not the case that at least 10 inches of rain fell today in Miami. So basically this will be that, okay, less than 10 inches of rain fell today in Miami. Okay, right? So so you can see, okay, we have given this solution. Okay, now similarly for the next example we can say what will be the so it is not the case that at least 10 inches rain fell in Miami. So basically we can also write this sentence as in this. Okay, in English also, of course, we know that we can speak same sentences many different ways, right? So okay, now what is the truth table of negation operator? So basically, if we have a proposition P, we know that either the truth value of this proposition P is true, or the truth value may be false. We represent true by T and we represent false by F. So what will be the truth? What will be the truth value for negation of P? So basically, if P is true, then negation of P will be false. Okay, if P is false, then negation of P will be true. So basically this is the truth table. Okay, this thing is called truth table. Okay, so basically what is the truth table? What is the definition of truth table? Truth table basically defines the behavior of some operator, okay, or some expression or some formula. For example, we have made this truth table for this operator, this negation operator. So this truth table is actually depicting the behavior of this negation operator. So this negation operator is basically complementing the truth value of the proposition. So for example, if I say some proposition P is my name is Deepak, then what will be we know that that is true. So now what will be the negation of p? Negation of p will be my name is not Deepak. Now of course that is false. So basically if p is true, then this negation of p will be false, and if p is false, then negation of p will be true. Okay, so these are the symbols, okay, for these are the different symbols. Sometimes they can use like this symbol is actually standard symbol in propositional logic, so that's why we have used this in the first place. And of course we can also write this in using p dash. P dash is also same thing. Similarly we can write it like p bar. P bar is also same thing, and similarly we can write it like this. Okay, so these are the different symbols that can be used. So we have given some these symbols. Okay, now what is the next thing? Now let's see the next connective. The next connective that we will see is conjunction. So we have already seen negation. Now we will see, okay, conjunction. So what is a conjunction? So basically if we have p and q are two propositions, then conjunction of p and q, okay, we denote that by p and q. Okay, so this symbol basically, okay, this symbol is for conjunction, or we can say and. Okay, so basically this is the conjunction. That conjunction is basically the name of this operator, or you can say that is the operation, and this is the symbol. Okay, so basically this is just a symbol that is actually used for this operation, and the operation name is conjunction. Okay, now what will be the conjunction of p and q? So for example, let's take this example. If we have two proposition, today is Friday and it is raining today, okay, then what will be the conjunction of these two? That will be today is Friday and it is raining today. So basically it is saying that, okay, basically this conjunction operator is actually nothing but p and q. Okay, also you can write it like p and q. Okay, both are same things, right? So we took two propositions. This is a proposition, this is a proposition, and we combined these two propositions using this operation. What is the name of this operation? Conjunction. And this is the symbol that is used for conjunction operation. So basically we get a new proposition. This is a new proposition that we get. And what is that new proposition? That new proposition is today is Friday and it is raining today. So that is a new compound proposition we have gotten. So now what is the truth table for this conjunction operator? So this the truth table will be, for example, if we have two proposition p and q, then we can make a truth table. Basically truth table is nothing but depicting the behavior of this conjunction. So basically let's make the truth table. So if both are false, like p is also false, q is also false, then okay, this is a very intuitive operator. Like if both are false, then their and also will be false. Okay, similarly if one of them is false, okay, if one of them is false and other is true, then also it will be false. Similarly if they both are true, then this will become true, right? So this conjunction operator, okay, this conjunction operation, okay, p and q is true when both are true, okay, else it will be false. So this is a very intuitive operator. Not all operators are this much intuitive. This is basically just the name. Okay, we are doing and of two things, so hence the truth value, okay, will be true if both are true, right? So we have seen this. Now let's see the next thing. Now so again these are the symbols. Some like for negation we use four symbols. Similarly for conjunction we can either use this is a very standard symbol, p and q, or we can write also, we can also write like this, okay, p and q, or we can just simply write pq. Okay, pq or we can write like p dot q. Like in mathematics many times you write if you have multiplication x, so this is the sign, this is the symbol of multiplication, but we can also write it like this, right? Because we just, okay, remove that. Okay, so basically similarly here this and we can write it like this, pq or p dot q. And also this and but, okay, they will have same meaning. So basically if I say p and q, okay, and if I say p but q, okay, both are same. Okay, so so basically this, if you see this word but in English sentence, then also, okay, you can just replace it with the this and. Okay, so they both have the same meaning for us. Okay, now let's see next operator, that is disjunction operator. Disjunction operator, this is also called or operator. So basically this says that p or q, okay, either p is true or q is true, so we represent it using this symbol. So this is the symbol, this v kind of symbol. Okay, this is a very standard symbol. Okay, p or q. Now so if we have two proposition p and q, then we can make a new proposition p or q. Okay, so it will be true when one of them is true. Okay, at least one of them is true. Okay, so for example, today is Sunday, and let's assume that p is today is Sunday and q is it is raining today. Then what will be p or q? It will be today is Sunday or today it is raining today. Okay, so basically it will be true if either today is Sunday or it is raining. Assume that both of these things are false, then it will become false. Okay, if it is not Sunday and if it is also not raining, then in that case this p or q will become false. So this becomes false when both are false. Okay, else it is true. Okay, so if at least one of them is true, then this p or q will become true. Okay, so so basically you can see that this disjunction operator, basically this is an inclusive or. In what do I mean by inclusive or? So this this disjunction operation, this is actually inclusive or. Inclusive or means if this is true, then this whole thing is true. If this is true, then also this whole thing is true. And if both of them are true, then also this whole thing is true. Okay, but there is there is one more thing, that is exclusive or. Exclusive or means exclusively exclusive, one of them must be true. For example, if p is true, q is false, then it will be true. Okay, if p is false, q is true, then it will be true. But if both are true, then it will be false. Okay, so this exclusive or is a different operation. Okay, this inclusive, so basically this disjunction is a operation. Okay, this disjunction we can also write it like inclusive or. These are the same things. Okay, inclusive or disjunction, these are same things. Okay, so and this exclusive or, this is a different operation. Okay, so let's see the truth table for these things. So okay, before going to that, let's see symbol for disjunction operation. We can either use this symbol, this is a very standard symbol, p or q. Okay, the name of this symbol is actually or. Okay, so we can also write it like this, p or q, or we can also write it like this, p plus q, because actually the behavior of this is disjunction operation is actually similar to the plus operation in mathematics. For example, you know that 1 plus 0 is 1, similarly 0 plus 1 is 1. Okay, so the behavior is now. Okay, of course you can say that 1 plus 1 is equal to 2, but no, you do not. Actually we are only having either true or false. So basically so in Boolean algebra, if you have ever if you have the knowledge of Boolean algebra, then we know that in Boolean algebra 1 plus 1 is 1. Okay, so so you can think of that in Boolean algebra we use this symbol for this or operation, right? In propositional logic we actually use this symbol. Okay, but actually any of these symbols could be used because they have the similar behavior. Okay, so as I have mentioned earlier, this Boolean algebra and this propositional logic, they are very similar thing. Okay, there is some difference, the small difference. Okay, what are those differences? Let me write it. Okay, so like in propositional logic we call true. Okay, in Boolean algebra we call 1. Okay, in propositional logic we call false. In Boolean algebra we call 0. In propositional logic we have and operation, operation. In Boolean algebra we have and operation denoted by dot. Okay, in propositional logic we have this or operation, and in Boolean algebra we have plus operation. Similarly, in propositional logic we have this negation operation, and in Boolean algebra we have some bar operation. Okay, so basically these are actually mainly used in propositional logic, and these are mainly used in Boolean algebra. So you can see there is there is very much similarity between these two topics. Okay, so if you understand one topic, then it is very easy to for you to understand the other topic. Okay, so now let's see the next thing. Okay, so we have already seen this, and now these are the truth tables for and or and so basically this is the truth table for conjunction operation. Conjunction operation is basically simple and operation p and q. Okay, this is a very intuitive, that it is true when both are true, else it is false. Similarly, disjunction operation also you can call it or operation. Okay, so this is true either p is true or q is true, or both are true. So basically you can see that this is true in all these cases. This is false only when both are false. Okay, now we have also seen this exclusive or operation, right? We have also seen this. Remember that this disjunction operation, this is also called inclusive or. This is also called inclusive or. So basically this inclusive or and disjunction operation both are same things. Now there is something called exclusive or. So exclusive or says that exclusively one thing must be true. Okay, it should not be like both are true. Okay, exclusively there should be some exclusive thing here. Okay, so exclusively one must be true. For example, here p is true, q is false, so it is true. Similarly, here p is false, q is true, so this is true. Okay, but you can see that in this case both are true. Since both are true, so this is false, because exclusively one should be true. Okay, similarly, if both are false, then of course then of course this is false. Okay, so this is the truth table for exclusive or, and this is the symbol for exclusive or. This is the symbol for exclusive or, a circle, and there is a plus inside that circle. So this is the standard symbol for exclusive or operation. Now let's see next. Yeah, so this next operator is very important. So all these operators that we have seen so far, they are intuitive, like p and q. Okay, like p or q. Okay, these are very intuitive, but this next operator, this is very important, and this is less intuitive than those other on those other operators. So this operator is uh, okay, let me write like here. Yes, so the next operator that we will see is implication operator. Okay, this is the symbol, this is just the symbol, and the name of the operation is implication. The name of the name of the operation is implication. So implication is the operation, and this is the symbol. Okay, so for example, if we have a proposition p and if we have a proposition q, then we can make a new proposition, new compound proposition. Okay, by using this operation implication. So p implies q. Okay, so this is a operation, this is the symbol of for this operation implication. Now so similarly we can think about when the truth table for this operation. Okay, when it is true. So the what does this statement say? This statement says that if p is true, okay, if p is true, if p is true, then q is true. Okay, so okay, just like we wrote p and q, then in the English. Okay, in English, how can we translate this? We can translate this using p and q. Okay, right? So p is true and q is true, we can write like this. So similarly, this statement, this p implies q. Okay, this operator can also be called implies. Okay, p implies q. Okay, so there are many other names we will see. Okay, for this same operation we have some other names also. Okay, so basically p implies q. Okay, how will we read this in English? We can read this like this: if p is true, then q is true. Okay, so basically we only care when p is true, then q should not be false. Basically that is the thing. For example, if you join some coaching, okay, let's take some example. Okay, if you join some coaching and that coaching institute says that if you for example, if you attempt all the 60 tests, okay, assume that they are giving some test series, and they are claiming that if you attempt all these 60 tests, then you will qualify in gate. Okay, so basically they are claiming that if okay, all 60 tests you attempt, all if all 60 tests you attempt, then so this says that then so okay, let me write it. Then you will crack gate. Okay, then you will crack gate. So this is the claim of that coaching institute. Okay, so now uh, okay, when will you feel cheated? Like after gate, if you could not crack gate, okay, but you did give these 60 tests, okay, then you will feel cheated. Okay, right? Because you will go and you will sue that coaching center. You will say that they said that okay, if I attempt all these 60 tests, then I will crack it. Okay, but I did attempt all those 60 tests, but still I could not crack gate. Okay, then of course that is a right, that then you can say that what they said was false, right? So now, but assume one scenario that you did not attempt those 60 tests. Okay, okay, now it does not matter whether you crack gate or not. You cannot say that that coaching institute claimed false. Okay, because that coaching institute says that if you attempt these 60 tests, then you will be able to crack gate. But if you do not attempt what about the case when you do not attempt these 60 tests? Okay, in that case the coaching center has not said anything. You can crack gate or you cannot crack gate. Okay, that does not matter, because basically you cannot say that that coaching center has cheated. Okay, so this is the behavior of this implication operation. Basically this implication operation is false only in one case, when p is true and q is false. Okay, so let's make a truth table for this. So if we have p and if we have q, okay, so let's make a truth table for this. So we can make what will be the p implies q, what will be this p implies q. So assume that both are true. Okay, p is also true, q is also true, then of course this is true. Okay, because p is also true, q is also true, so this is true. Similarly, assume that p is true and q is false. Now in this situation this is false, because we have already seen that this statement says that if p is true then q must be true. But in this case you can see p is true but q is false, hence of course this is false. Okay, in all other cases, for example, if p is if p is false, okay, if p is false, then we do not care about q. Okay, q can be true or q may not be true, we do not care. So basically if p is false, then q can be anything, we do not care, and this implication this is true. So I hope you understood. So basically this implication operator, this implication operation says that if p is true, then q should not be false, right? Okay, but it is not saying anything when p is not true, right? So basically this is not saying anything about that, right? So let's see in the truth table for this. So this is the conditional statement. Okay, this is the theory. So if p and q are proposition, then conditional statement p implies q. Okay, this is the symbol for implication operation. Okay, so we can either we can use this symbol, or we can use this single arrow symbol. Okay, so these are okay, same symbol is the proposition. If p then q. Okay, now okay, this is false only when p is true and q is false. In all other cases it is true. Okay, and this is actually in such implication statement, this p, okay, the p is on the left hand side of this implication operator. So this p is called hypothesis or premise. Okay, and this q is called the conclusion. So basically what was the like in the coaching example we took, what was the hypothesis? Hypothesis was that if you attempt all the 60 tests, so that was the hypothesis. Okay, and what was the conclusion? Conclusion was that you can crack gate, you will crack gate. Okay, so that was conclusion, right? So now of course what is the truth table? So we have already seen the truth table for this. So truth table is this, and remember that implication operation is false only in one case, when P is true and Q is false. Else, okay, so basically we can also write it like this. So if we have P implies Q, then it is true. Okay, it is true when if P is false. What about when P is false? If P is false, then this is automatically true, because when P is false, then we do not care about Q. Okay, so if P is false, so basically if P is false, then this P implies Q, this P implies Q will become true. Or if Q is true, you can see from this truth table. So if Q is true, you can see from this truth table that when Q is true, then also this P implies Q is true. Okay, so we can say that this P implies Q is true when either P is false or Q is true. Okay, so we can also write it like this. So basically we can write it like this: P implies Q is true when either either P is false or Q is true. Okay, so remember this thing. Actually, this is a very important operator. This is not, this is less intuitive. That's why we took some example, and that's why we spend some time on this operator. But this is a very important, and even if you did not intuitively understood the behavior of this operator, slowly you will understand. Okay, till then you just remember this, that this P implies Q, this is false only when P is true and Q is false, right? In all other cases, this P implies Q is true. Okay, so so this is a very important operator, and so now this we have already seen. Then note that the statement P implies Q is true when Q is true or P is false. Okay, so we can also write it like this: P implies Q. We know that this is true if and only if P is false or Q is true. Okay, this is the symbol for or, that disjunction. Okay, and this so basically what does this mean? This means that either P is false or Q is true. Okay, so we know that this is the behavior of implication operation. Okay, so this is a very important formula. This P implies Q. Okay, this statement can also be written like this. So basically this statement is equivalent to this statement. So P implies Q, basically this is same as P dash plus Q. Okay, so this P dash plus Q actually says that either P is false or Q is true. Now again, since this okay, this implication, this conditional operation, okay, this implication operation, there are many names. Okay, so either we can say it conditional operation or we can say implication operation. Okay, both are same thing. So this is a very important operator in mathematics, in discrete mathematics, and in computer science we use it many times. So there are many terminology, there are many equivalent ways to say to interpret this P implies Q in English. Okay, so in English what we can say, for example, if I give you this, okay, if I give you this, okay, P implies Q, if I give you this, then you can interpret this in English in many ways. The first way is the first way that we have already seen: if P then Q. Okay, if P then Q. Okay, so basically this means that if P is true, then Q must be true. Now the next way, and the next, okay, is P implies Q. Okay, the next, so P implies, we have already seen this. Okay, if P then Q, so we can remove that then, and so this will if P Q. Okay, this also means that, okay, if P is true, then Q is true. Now, okay, now this is P only if Q. Okay, we will see this. Okay, we will also see this, we will also see this. Now so we will see these okay, shortly. So okay, don't worry about these three, but okay, you can easily understand this. This is basically, we have just reversed this: Q if P. So what does this means? That Q is true if P is true. So basically we can also write it like if P Q. Okay, both are same thing. Okay, this seventh statement and this third statement are same. Okay, now the next is Q whenever P. So this remember that in mathematics, in discrete mathematics, this statement when, this is similar to if. Okay, this is similar to if, and this is similar to whenever. Okay, so all these things have the same meaning. Okay, when, if, whenever. So, earlier we have already seen that this but has the same meaning as and, right? So basically these kind of things. Okay, so for example, q whenever p, so you can replace this whenever by if. Okay, and you will get the seventh statement. Similarly, you can replace this when by if, and you will get the seventh statement. We will see this shortly, and we will also see this shortly. Now this again, q follows from p. Now of course we know the in english what is the meaning of follow. So basically if I say that q follows from p, that then means that q actually is following p. Okay, so basically this statement also says the same thing. Okay, now this unless. Okay, in mathematics, in discrete mathematics, this unless will be same as or. Okay, so these kind of things. Okay, unless will be same as or. Okay, but will be same as and, if will be same as whenever, whenever will be same as if, and these kind of things. Okay, so now all the statements that we have we have skipped. For example, this fifth statement, sixth statement, 10th and 11th. So let's see them. Okay, so let's see them by one example. Let's take one example. Let's assume that p is x equal to 2, and let's take q is x is even. Now what will be this p implies q? P implies q will become, if x equal to 2, then x is even. Tell me, is this statement true or false? So you can see that if x equal to 2, then x is even. Of course we know that this is true. So can I say one line? Can I say this, that x is equal to 2 is sufficient to say that x is even? Can I say this? Right, because if x is equal to 2, then it is sufficient to say that x is even. Okay, so basically I can say that this x equal to 2 is sufficient. Okay, is sufficient for x to be even. X to be even, right? I can say this, right? Because if x equal to 2, then x is even. So x equal to 2 is sufficient for us to say that x is even. Now uh, now take now assume this, is this necessary? Is this necessary? X equal to 2, is this necessary for x to be even? No, right? Because this is not a necessary thing. For example, even if x is not 2, if x is 4, then also x is even. Okay, so you can say that x equal to 2 is not necessary. Okay, you can also have other values for x, which will make x even. Okay, so basically we can say that x equal to 2 is sufficient, but x equal to 2 is not necessary, right? Similarly, in the other direction, assume that, okay, is this is this thing x is even, is this thing necessary for x equal to 2? Right, this is necessary because when x equal to 2, then x will definitely be even. Okay, so we can say that this x is even, this is necessary for x equal to 2. Okay, but so we will take some other example, and we will see that, okay, this is actually so basically this x equal to 2 is sufficient for this. Okay, and this thing is necessary for this. Okay, so that is what we can write for p implies q. Okay, I have taken this example to to give you some intuitive understanding. Okay, about this implication operator. We can also write, for example, this formula in english. We can also write it like this: p is sufficient for q. Okay, what we can write: p is sufficient for q. Okay, also we can write it, okay, so p is sufficient for q. Also we can write it like this: q is necessary for p. Q is necessary for p. Okay, so these things we have seen, we have written in this previous slide. So you can read this fifth point: p is sufficient for q. Okay, p is sufficient for q. Also, of course, this same line can be written like this: a sufficient condition for q is p. Okay, these two are same thing. Okay, similarly you can see here q is necessary for p. Also we can write the same line using this: a necessary condition for p is q. Okay, so I know it might be hard if you are studying this thing for the first time, but don't worry. You can just rewatch the lecture if you have not understood this, and you can understand these things. Okay, so basically these 13 English sentences I have written, all these English sentences are actually English interpretations for P implies Q. Okay, so basically that P implies Q, we can interpret that in 13 ways. Okay, so that is why this implication operator is so much important, because it is used in discrete mathematics or in computer science very much. And we can have these kind of different English statements for this one thing, this P implies Q. Okay, for other operators, for example conjunction, disjunction, we did not have these many variations. Okay, so now the only case that is remaining is this P only if Q. Now this P only if Q, you know that this only if thing, only, what is the meaning of only if? Only if means necessary, right? So basically only if gives the same meaning as this necessary. So when we say that P only if Q, that means that Q is necessary for P. Okay, so this fourth statement and this 10th statement, they are same. Okay, P, so basically what it is saying, it is saying that P only if Q. So basically it is saying that P is true only if Q is true, right? So basically it is saying that Q is actually necessary for P. Okay, so we have already seen, this 10th statement, and this 10th statement is same as fourth statement. Hence, okay, we have seen all these 13 statements. Okay, so remember some things like this: unless actually has the same meaning of or. Okay, unless gives the same meaning of or. Okay, similarly this but gives the same meaning of and. Similarly this when gives the same meaning of if, and so on. Okay, so okay, for this example, consider this example: x equal to 2, x is even. For this example, okay, when where P is 2 and Q is x is even. For this example, this is the whole theory that so this is the theory. I have also written it in these slides, but we have already explained it. Okay, so you can read it out. Okay, and just give me 1 minute. Okay, read it out and understand this sufficient and necessary thing. Okay, just give me a second. Yeah. Okay, so let's move further. Okay, so let's take some exercise for this implication operation. This implication operation is very, very, very important. That's why we are spending so much time in this operation. So let's take this example. All other operations that we have studied, like conjunction, disjunction, these kind of things, they are intuitive, and we do not need to spend much time in those operations. Let's take this example. Which of the following statements are equivalent to if x is even then y is odd? Okay, So basically what we have if x is even then y is odd. Okay, so we can solve this using like this. Okay, let's assume that p is a proposition. Okay, p is a proposition for p is a proposition for this statement that x is even. X is even. Okay, and let's assume that q is a proposition for y is odd. Y is odd. Okay, so let's assume that these are the two propositions. Okay, now since it is saying that which of these following statements are equivalent to if p then q. Okay, so basically what we can write it like this: if p then q. So basically he is asking p implies q. Okay, so basically in this question he is asking which one of these statements actually is the correct interpretation for this p implies q. Remember, this p is nothing but x is even, and this y this q is nothing but y is odd. Okay, so let's see this first. Y is odd only if x is even. Okay, let me give you a trick before that. Okay, let me give you a trick before that. We have already seen that this p implies q, we can write it like this: p only if q. We have already seen this, right? So we have seen that this p implies q, we can write it like p only if q. So the trick is that, okay, what is the trick to remember? Okay, basically we have it is not like you don't need to by heart this, you don't need to by heart this. We have already explained the logic, but if you are in exam and at that time you do not if you do not remember whether this gives whether this only if goes this side or this side. Okay, if you do not remember that, okay, then if you just start remembering the logic, okay, then it will consume time. Okay, so it will be beneficial if you can quickly see this only if. So what is the way? The way is that only if goes forward. Okay, remember this trick. Okay, this trick, what is the trick? If we have a statement p only if q, so basically there is p, there is q, and in between we have only if, then we can replace this only if with forward implication. Okay, and remember, if we have something like p if q, if p if q, okay, p if q, okay, then since we have this p, this q, and in the middle we have if. Okay, so this if goes forward, this if goes forward. So this is a trick. Okay, we have already explained how these things work, but this is a trick to remember. Okay, so so basically whenever whenever you get confused with what to write, then what you can do like this: you can write p q, and in the middle you can write only if. Then only if can be replaced by forward implication, and this if can be replaced by backward implication. Okay, so for example, what will be this statement? Okay, what will be the one statement? What will be this? So okay, only if is in the middle, right? Only if in the middle. So what we can say, only we can replace this only if by forward implication. Okay, and this side, okay, what is this side? Y is odd. What is y is odd? Y is odd is basically q. Okay, and x is even. What is x is even? Okay, x is even is p. So basically this first statement actually is q implies p. This is not p implies q. Okay, so one more thing I would like to mention is that for example, yeah, so we already have seen a few operations, like we have seen this conjunction like p and q. Okay, remember that this p and q, okay, is commutative. For example, this p and q is same as q and p, right? Because what is this p and q? This p and q is basically just okay, p must be both must be true. Okay, similarly this q and p, so basically these are same thing. P and q is same as q and p. Okay, so basically we can say that this conjunction operation is commutative. Okay, this property is called commutative property. Basically we can just interchange. Okay, so p and q is same as q and p. Similarly for disjunction also we can do this. Okay, disjunction is also commutative. So p or q is same as q or p. okay. But this implication, like, okay, P implies Q, okay, this is not commutative. This is not commutative. So basically we can say that P implies Q and Q implies P, both are okay. It is not necessary that they both are equal, okay. They may be equal, but it is not necessary. For example, for disjunction and for this conjunction, it is necessary that both are same, okay. How can we prove that this implication operation is not commutative? So we can make a truth table, okay. We have already seen what is a truth table. Truth table is basically nothing but it depicts the behavior of a operation. So let's make a truth table for P implies Q, okay. Then we will make a truth table for Q implies P, okay. So if these two things, P implies Q, Q implies P, if they are same, then their truth table also must be same, right? So let's make a truth table for this. Let's make so basically either P or Q can be false false, or they can be false true, or they can be a true false, or they both can be true true. So we have considered all the cases, okay. So now what is the truth table for this P implies Q? We have already seen this P implies Q is always true except in one case. What is that one case? That one case is this. So basically when P is true, Q is false. In this case we can say that this is false. In all other cases, okay, we know that this P implies Q is true, right? So this is the truth table for P implies Q. Now let's make truth table for Q implies P. Now what will be the truth table for Q implies P? Remember that this Q implies P is false only when Q is true and P is false, right? So basically this Q implies P, when it is false when Q is true and P is false. So basically in this case when Q is true and P is false, so in this case we can say that this is a false. In all other cases this will be true. So basically you can see that this truth table, okay, and this truth table, both are different, right? This is true true false true, this is true false true true. So you can see that these are different. Hence we can say that this implication operation is not commutative. So basically P implies Q is not equivalent to Q implies P, okay. These two are not necessarily same thing, okay. They can they are different things, okay. Occasionally they may be same, okay, occasionally they may be same, but it does not matter. We can say that this implication operation is not commutative, okay. Now let's go back to our example. So this first statement, basically we have seen that this is Q implies P, okay. So of course this is not equivalent to P implies Q. Basically we want to interpret this P implies Q, okay. But this is not a correct interpretation. So you can say that this one is not a equivalent, this is not a correct interpretation for this P implies Q. Now what about the second one? X is even is sufficient for Y to be odd. Now again, so basically we can write it like this: X is even. What is X is even? X is even is P. So basically P is sufficient for Y to be odd, okay. So this sufficient goes forward, okay. Again some more tricks we can see. So just like for only, if we have seen the trick, and similarly for sufficient also we can see the trick. So sufficient goes forward and necessary goes backward. So basically if we have a statement like P is sufficient for Q, okay, remember P is sufficient for Q, then this sufficient can be replaced by forward implication, okay. If we have a statement like P is necessary for Q, then this necessary can be replaced by backward implication, okay. So okay, you might be feeling that you okay, I'm telling you to buy hard these things. No, I'm not telling you to buy hard these things. We have already explained these things. We have already explained that this P implies Q can also be called that P is sufficient for Q. We have already explained that using an example, okay. But the thing is that if you remember these tricks, then it will be time saving for you in the exam, okay. So these small tricks, and if you practice more and more, then these tricks will be in your subconscious mind. Even if you are half asleep, then also you can you can answer these things. Okay, so basically what will be this? X is even. What is so we have already written this x is even is basically nothing but p. Okay, we have represented this x is even by this proposition p. It's sufficient. Okay, it's sufficient can be replaced by forward implication. And y to be odd, y is odd is nothing but y. So basically you can see p implies y. Okay, so this is what we wanted, so we can say that this is a correct, this is a correct interpretation. Let's see this. X is even. Okay, is necessary. We know that necessary goes backward. Okay, so basically this is p, this is backward, this is q. So basically what we got p, and this is backward, this is q. So basically this thing is same as q implies p. Okay, so we already know that this is not equivalent to p implies q, so you can say that this is also not correct. Okay, next, if x is odd then x is even. So what is this? X is odd. Remember that p is x is even. So what will be x is odd? X is odd is nothing but p bar, right? So basically what I can write, if x is odd, okay, then we can say that x is odd implies y is even. Okay, so p bar implies y bar, p bar implies q bar, right? So again, okay, we will, okay, this is actually the inverse, and this inverse is not equivalent to p implies q. Okay, so let's see this also. Okay, so basically what we are saying, we are saying that there is something called p implies q. Okay, so we have already seen, I told you that this is a very important formula, that this p implies q can also be written as p dash plus q. We have already discussed this. Okay, basically p implies q, basically when is this true? This is true when either p is false or q is true. So basically this p implies q can be written as p dash plus q. Okay, this thing and this thing, they both are same. Okay, they both are equivalent. Okay, now what will be the expression for p bar q bar? Okay, what will be the expression for this? Okay, similarly you can see that, okay, similar to this, like p implies q can be written like p dash plus q, then what can be written like this? So basically we can write it like this. Okay, p bar whole bar, okay, p bar whole bar plus q bar, right? Okay, so basically the same. Okay, p implies q, we wrote it like p dash plus q. Similarly p bar implies q bar, so we can write it like this. Now what is this? This is nothing but, what is p bar bar? So basically this is p. Okay, and this is plus q bar. You can see that these two things are different. Okay, this is p dash plus q and this is p plus q dash. Okay, so these two things are different, so we can say that this is not equivalent to this. Okay, this is not equivalent to this. What about what about q implies p? Okay, we have already seen that this q implies p is not equivalent to p implies q. But okay, how can we write it? We can write it like this, q dash plus p, right? Okay, so similarly what about this not q implies not p? Okay, one thing you can note that I am, okay, interchangeably using, sometimes I'm writing p dash, sometimes I'm writing not p, sometimes I'm writing p bar. Okay, so because I have already told you that these are same things. Okay, so basically this thing is same as writing q dash. Okay, so now, okay, what will be this equivalent to? So this q dash implies p dash. Okay, we can write it like this, we can write it like this. Okay, q dash whole dash, okay, q dash whole dash plus p dash. So what will be this? This will be p dash plus q, right? You can see one thing, that this is p dash plus q and this is also p dash plus q. So you can see that this p implies q, this p implies q, this is equivalent to not q implies not p. Okay, so basically this p implies q is equivalent to when we interchange them and complement both of them. For example, we interchange q and p. Okay, and we complemented both of them. So we can say that this thing is equivalent to this thing. Similarly, this is p plus q dash. Okay, and this is also p plus q dash. So we can say that these two things are also same. How can you say? Okay, consider this. q implies p. Okay, so this will be equivalent to this statement. Why? Because we have already told you that you can just interchange them and complement both of them. So okay, if you interchange them, then you will get p implies q, and if you complement both of them, then you will get p bar implies q bar. So that's why these two things are equivalent. Okay, similarly this thing and this thing are equivalent. Okay, so now you can solve this question very easily. We have already solved okay, we have already seen all the things required to solve this question. So now this statement basically becomes p bar implies q bar, and this p bar implies q bar is not equivalent to p implies q, so this is also not the answer. Similarly, this is x is even and y is even, so this is basically nothing but p and q bar. Okay, because q is y is odd, so q y is even will become q bar. Okay, p and q bar. Okay, so this is also not equivalent. Next, x is odd or y is odd. Okay, x is odd. What is x is odd? X is odd is nothing but p dash. Okay, and or y is odd is nothing but q, so p dash plus q, and we already know that this p implies q is the same as p dash plus q, so this is also correct. Okay, so only two the second and sixth statement are equivalent to p implies q. Okay, so I hope you understood all these things. Okay, but even if you did not understand, this is a very important operator and it is a confusing operator. That's why we are spending so much time. And you can, if you did not understand anything, then you can just rewatch the lectures and you can understand them. And we will solve many questions, and we will take some many practice questions, and you will be familiar with these things, and they will be on your fingertips. Okay, so don't worry. So some important results on implication operation. This result we have already seen. P implies q. Okay, this is same as p dash plus q. Okay, next thing, this if p is true, then this thing. Okay, so we this thing, remember that. Okay, what about this thing? We can write p implies q. Okay, if we have p implies q, we can write it this like this, p dash plus q, right? Okay, so p dash plus q. Now if p is true, okay, what will happen if p is true? If p is true, then what will happen to p dash? This p dash will become false, right? And false plus q. Okay, false plus q. Okay, so if we have some false plus q, then this is same as q, right? Because if you just or with plus, then you will get the same thing. Okay, q. Okay, so we will see these properties, but this is a very intuitive property. Basically, if this is false, assume that q is false, then what will happen? You will get false. If q is true, then you will get true. So basically, whatever the value of q is, you will get that value. So false plus q is same as q. Okay, so now if in this second statement, if p is true, then this thing will become false, hence the complete thing will become q. So basically, you can say that if p is true, then p implies q is same as q. Okay, so similarly, if q is false, what will happen? If q is false, then if q is false, then this thing will become false. Okay, then this whole thing will become p dash. Okay, so you can see this. If q is false, then p implies q will become p dash. Okay, so these are very simple results actually. Okay, if p is false, then what will happen? If p is false, then this thing will become true, and true plus anything will become true. Okay, so you can say that if p is false, then this thing will become true, and if q is true, then this thing will become true. Okay, so you can either using this you can prove it, or you can intuitively understand this. Like if we have p implies q, we have already told you that this p implies q. If p is false, assume that p is false, then what will happen? If p is false, then this whole thing will automatically become true, right? Because if p is false, then we do not care about the value of q. Q either can be false or q can be true, we do not care. This whole thing will become true. Okay, so that is what we have written in this fourth statement. If p is false, so basically if p is false, then this whole thing will become true. Okay, similarly, we have already seen that if q is true, then also this whole thing will become true. So that is what we have written in this fifth statement. If q is true, then also this whole this p implies q, this whole thing will become true, right? So So these are some important results. Okay, so okay, you might not remember them right now, but once you practice very much, then these things will be on your fingertip. And these points, okay, we have already explained how these points are true. Okay, we have already explained the proof of these statements, but it would be beneficial if you okay, if you understand how to prove them, and also you remember them on your fingertips. Okay, so now let's go further. So okay, and this is some simple example we have already seen. For example, if let P be the statement Maria learns discrete mathematics, and Q be the statement Maria will find a job. So what will be P implies Q? So we can write it P implies Q also so all these are okay. So for example, we can write it like this: if P then Q. So basically, if Maria learns discrete mathematics, then Maria will get a good job. Okay, so this is the so basically all of them are correct interpretation for P implies Q. Okay, so the next interpretation that we can have is Maria will find a good job when. Okay, this when can be replaced by if. Okay, and I have already told you that this if actually goes backward. Okay, so basically this was also same thing. Okay, similarly also we have already seen that this if pq, if pq, okay, we can also write it like this: q if p. Okay, we have already seen this. Okay, so so basically this is that. Now similarly, for example, this it is sufficient for her to learn discrete mathematics. Okay, we already know that p implies q can be written as p is sufficient condition for q. Okay, so that is what is written here, that it is sufficient for her to learn discrete mathematics for her to get a good job. Similarly, similarly, okay, you can write it like this: Maria will get a good job unless she does not learn discrete mathematics. We already know that unless is nothing but or, so you can replace this unless with or. Okay, you can replace this unless with or. Okay, what is this? This Maria will find a good job, this is nothing but q. Okay, and what is this? This is she does not learn discrete mathematics, this is nothing but p dash. So we have got q plus p dash, and we already know that p dash plus q is nothing but p implies q. Okay, so this is also equivalent to p implies q. Okay, so these all these four statements are correct interpretation for p implies q, where p is Maria learns discrete mathematics and q is Maria will find a good job. Okay, so we are taking more and more example, so that even if you did not understand, then you can understand. So even if you if you have some doubt, then we will discuss it on WhatsApp group, and you can personally ask me. Okay, or if you have any doubt right now, and if you feel that you cannot proceed further with that doubt in mind, then kindly ask me. Okay, I'll wait for 5 seconds. If you have any doubt, you can ask me, else we will just proceed. Okay, so if you have any doubt, then you can interrupt me and you can ask me. Okay, so let's move forward. Okay, these are some kind of things, like if we have a conditional statement. Okay, we have already told you that this implication statement is also called conditional statement, because there is a condition. What is the condition? The condition is that if p is true, then q must be true. So that is a condition, right? Okay, it cannot be the case that p is true and q is false. Okay, that case is not allowed. Why? Because that case will make this thing false. Okay, so we already know these things. So basically this is a conditional statement, this is an implication statement. Okay, and uh, and we can so basically we can write it like this. Okay, if p then q, we have already seen these things. Okay, these are very basic things. If p then q, so basically p implies q, we can write. Now there is something called if we have a conditional statement of this form, then we can write a converse statement of that. Okay, we can write converse statement. So what is a converse of a conditional statement? So if we have a conditional statement, this p implies q, then converse will become q implies p. Okay, then converse will become q implies p. Okay, similarly the there is something called contrapositive. So for example, if we have p implies q, then the contrapositive of this will become q dash implies p dash. Basically we interchange p and q and we complement both of them, so then we get a contrapositive statement. Similarly we have an inverse statement. Okay, if we have a conditional statement p implies q, so basically p implies q is a conditional statement, then the inverse of this conditional statement will be not p implies not q. Okay, so just complement both of them. Okay, so these are the three important new propositions basically we are making from this conditional statement. So if we have a conditional statement, then we get three new conditional statements. Okay, and we have already seen, I have already told you that this p implies q, this is equivalent to q dash implies p dash. We have already seen this. How did we see this? Okay, we have already seen this p implies q is nothing but p dash plus q. Okay, this is nothing but p dash plus q, and this thing, what will be this thing? This will be also will become p dash plus q. Okay, so basically you can see these things are equivalent. So you can say this p implies q is equivalent to q dash implies p dash. Now what is q dash implies p dash? You can see that q dash implies p dash is contrapositive. So basically we can say that any conditional statement is equivalent to its contrapositive. Okay, similarly we have already seen that this statement q implies p is equivalent to not p implies not q. So basically what we can say, for any conditional statement, its converse and its inverse will be equivalent. Okay, so basically converse and inverse will be equivalent, and the original conditional statement and its contrapositive will be equivalent. So we have written these theorems here. Okay, we have already explained all these things that we have written in this slide. Okay, so we already okay, we are again and again we are using this formula: p implies q is nothing but p dash plus q. Okay, so this p implies q is nothing but the original conditional statement. Now what we can do, we can make contrapositive statement. How can we make contrapositive statement from p implies q? So if you have p implies q, then contrapositive will be, you can just interchange them and then complement them, so you will get. Hello, is someone is speaking? Okay, so let's okay, so yeah, this so contrapositive of p implies q will be q dash implies p dash. Okay, so so what we have already seen, that a conditional statement is equivalent to its contrapositive. Similarly we have already seen that a converse of a conditional statement is equivalent to inverse of that conditional statement. So basically if you have conditional statement p implies q, then its inverse and its converse, they will be equivalent. Okay, and also this is a very important thing, that a conditional statement is not equivalent to its converse and or inverse. We have already seen that a conditional statement is equivalent to its contrapositive. Okay, and we have already seen that if we have a conditional statement p implies q, okay, then this is not same as q implies p. So basically this is converse and this is the original conditional statement, and we can say that they are not equivalent. Okay, so next what is the next thing that we can see is, okay, so this is some example. The original statement that we have is, if this book is interesting, then I am staying at home. Okay, if this book is interesting, then I am staying at home. This is the original conditional statement. And what will be the converse of this statement? So what will be the converse? So for converse, all you have to do is just interchange p and q. So what will be the converse? It will become, if I am staying at home, then this book is interesting. So basically we have just interchanged, if this is p and if this is q, then all you have to do is just interchange p and q, and you will get a converse, because we already know that if we have original conditional statement p implies q, then the converse of that statement will be q implies p. Okay, now what will be the inverse? For inverse, all you have to do is just complement them. For example, if this book is interesting, then I am staying at home. So inverse will become, if this book is not interesting, then I am not staying at home. This will be inverse. Okay, now what will be the contrapositive? Contrapositive will be basically you just interchange them and then you complement them. So what will it become? It will become, if I am not staying at home, then this book is not interesting. Okay, and we have already seen that any original statement is equivalent to its contrapositive, and we have already also seen that a converse and inverse are equivalent. So basically these two things are equivalent, and similarly these two statements are equivalent. Okay, so so this is an example for converse, inverse, and these kind of things. Okay, now there is this example for practice. Okay, if P is the statement, I will prove this by cases. Okay, Q is the statement, there are more than 500 cases. R is the statement, I can find another way. Okay, so these are three propositions. We are given three propositions, and the first question he is asking is state this in English. Okay, so what will be this? Okay, what will be this? This will be, okay, basically this thing is implying this thing. Okay, so we can write it like this: if this, okay, if this, then P. Okay, we can write it like this, right? Now what is this? This is either R is false or Q is false, then P is, then P is true, right? So we can, what we can say, we can say that what is R is nothing but I can find another way. So we can say uh, if I cannot find another way, or there are or it is not the case that there are more than 500 cases, then I will prove this by cases. Okay, so basically we have just, okay, a simple English translation. Okay, so now okay, we will see in the next slide. Okay, it might be confusing because three propositions are involved. Okay, so let's see if this, okay, state the converse of statement 1 in part 1. Okay, so what will be the converse? For example, if we have not R, okay, or not Q, okay, implies P. So tell me, what will be the converse? So we already know the converse is converse of this statement will be just interchange them. So converse will be P implies this thing. Okay, what thing? R dash or Q dash. Okay, so this will be the converse. Okay, so in English, how can we interpret? We can interpret like this: if P, or what is P? P is nothing but I will prove this by cases. So basically we can say, if I will prove this by cases, then it implies, then either R is false or Q is false. Okay, similarly what is the inverse of this statement? So inverse, for inverse, all you have to do is just negate this and also complement this. Okay, so what will be the inverse? You can just negate this, you can also negate this. Now what will be the contrapositive? For contrapositive, you have to, okay, exchange this here, and then you have to complement them. Okay, so in the next slide we can get the answers. Okay, now what will be the first? The first is nothing but, if I cannot find another way, or there are not more than 500 cases, then I will prove this by cases. Okay, now this is converse, this is inverse, and this is contrapositive. Okay, so okay, so this is a very simple example. You can practice this, you can practice it later. Okay, now let's move on. Now the next thing is biconditional operations. So three operations are okay remaining. So okay, let me quickly go through them. So okay, we have already seen some operators. For example, we have already seen negation operator, conjunction operator, disjunction operator, implication operator, and also we have seen exclusive or operator. Okay, operation. So these five operations we have already seen. Okay, there are three more operations. Okay, one is biconditional. Okay, so basically this is biconditional. So basically this is one way, and you can see this is two way. Okay, there is another operation called NAND operation. Okay, NAND operation. So this is the symbol for NAND operation, and there is something called NOR operation, and this is the symbol for NOR operation. So let's see. Okay, we have already seen these five operations. Let's see this operation, which is nothing but biconditional operation. Okay, so basically if we have some proposition P and if we have some proposition Q, then this we can make a new proposition, that is P and this is biconditional Q. Okay, how will we interpret this? We will interpret this like this. Sorry, we will interpret this like this. Okay, P if and only if, P if and only if Q. Okay, so basically if we have this statement if we have, then we can interpret this statement like this. Okay, P if and only if Q. Why? Because basically you can see that this is a by implication, basically both sides implication is there, so we can also write it like this: P implies Q, okay, and Q implies P. Okay, so basically this is the meaning of this. Okay, this is the so basically you can see P by conditional Q. Okay, so both sides, okay, this way and this way, both sides we have implication, so we can write it like this. Okay, P implies Q and Q implies P, basically both sides must be true. Okay, so that is this is the operator. And how do we interpret this? We interpret this like this: P if and only if Q. Okay, so okay, if you remember, then what was P implies Q? What was P implies Q? If you remember, then you can just simply you can know that this was P only if Q. If you remember this, P only if Q. This was this, right? P only if Q, because we had already told you that only if goes forward, right? So this P implies Q was P only if Q. Okay, but this was one way implication. Okay, this was one way implication, but if you see this is two way implication. Okay, so this is if and only if. Now remember that this only if means this goes forward, and we have already told you that if goes backward. So basically we are going forward also, we are going backward also, so basically we can say that P implies Q and Q implies P. Okay, so this is the operation by conditional operation. Now we can see this. So if we have P and Q are two proposition, then by conditional statement this is by conditional P by conditional Q. Okay, or we can say P double implies Q. Okay, because both way we are implying, so we can write it like this: P if and only if Q. Okay, so now what will be the truth table for this? So the truth table for this we can okay, we will get it the truth table. But okay, remember this: P double implies Q is basically nothing but P implies Q and Q implies P. And also if and only if, this also, okay, we sometimes we just write it in short I double F. Okay, so basically I double F means if and only if. Okay, so let's see what is the truth table for this. Okay, so let's see what is the truth table for this. So this is the truth table. So what is the truth table? Basically truth table is you can see that P if and only if Q. So basically this is true when either both P and Q are true or both are false. For example, if they both are true, then this is true. You can see that if they both are false, then also true. But if one of them is true, one of them is false, in this case you can see this is false. Okay, how can you, okay, let's see okay, let's see. We have already told you that this P implies Q is nothing but this P implies Q is nothing but we have already told you P implies Q, sorry, P double implies Q is nothing but P implies Q and Q implies P. Okay, so if you remember the truth table for P implies Q, the truth table for P implies Q was if you remember that, then that was true, false, true, true. Okay, that was the truth table for P implies Q. Okay, so basically P implies Q was false only in this case when P was true and Q is false. And what is the truth table for Q implies P? So Q implies P, the truth table will be true, true, false, true. Now you can just make a truth table for this P implies Q and Q implies P. How can you make a truth table? So just apply the conjunction operation. If you already know that conjunction operation is true when both are true. Okay, so in this case conjunction operation is false, in this case conjunction operation is false, and in this case also conjunction operation is true. So again we have gotten this and this truth table. So okay, this is the proof that okay, P by conditional Q is basically same as P P implies Q and Q implies P. Okay, So now these okay, we saw some 13 interpretations for p implies q. Okay, so similarly for p double implies q also we have some 5 interpretations. Okay, so what are those interpretations? We have one interpretation we have already seen, and that is p if and only if q. Okay, the other interpretation is p is necessary and sufficient for q. We have already seen that p implies q. Okay, how can we write p implies q? We can also interpret that as p is sufficient for q. Okay, but in this situation we know that p implies q and q implies p, so we can say that p is necessary and sufficient for q. Okay, also we can since okay, this is commutative. Remember this this p double implies q, this is commutative. This p double implies q, this is commutative. So basically p double implies q is same as q double implies p. Okay, so basically you can just interchange p and q. Okay, so basically if you interchange p and q in this first statement, then you will get this third statement. Okay, similarly you can interchange these p and q in this statement, then you will get q is necessary and sufficient for p. Okay, also this is a short version, p I double f q. Okay, this I double f is nothing but if and only if. Okay, also this is this kind of statement like p follows from q and vice versa. Okay, what is this p follows from q? Sorry, this q follows from p, this is nothing but q, p implies q. We have already seen this in implication operation, that q follows from p actually is nothing but p implies q. Okay, and vice versa. What vice versa means? Vice versa means that you can also okay go this side. So basically p implies q and q implies p. Okay, so this was by conditional operation. This was also very important operation. Okay, so these two operations, this implication operation and this by implication or by conditional operation, these two are very important operators in this first order logic or mathematical logic or propositional logic. So basically now the next operation is NAND NOR operators. Okay, these are not very important, but okay, let's see this. In Boolean algebra we use these operators, this NAND operator and NOR operator. If you have the understanding of Boolean algebra, then you already know that and this NAND actually is nothing but not and. Okay, basically you can write this this NAND you can write like not and. So basically what we do, we first and then we not. So basically if we have p NAND, okay, this is the symbol for NAND. Okay, in propositional logic. Okay, in propositional logic this is the symbol for NAND. Okay, so how can we write this? We can write it there like this. Okay, p first we can AND them and then we can not them. Basically even the name of this NAND this AND actually stands for not, and this AND stands for AND. Okay, so this p and q and then we not it. Okay, so now this is same as p or p dash or q. Okay, this is the De Morgan formula. We will see it shortly. So there is something called De Morgan formula. Okay, what is De Morgan formula? De Morgan formula is like this. If we have p and q the whole complement, okay, so then we can write it like this. Okay, p dash plus q dash. Okay, remember that I'm interchangeably using this for example, this plus is nothing but the disjunction operation. Okay, I could also write it like this, p dash or q dash. Okay, these are the same things. Okay, so I'm interchangeably using these symbols. Okay, so this is the De Morgan formula. What is the De Morgan formula? This. Okay, so p and q complement, whole complement. Remember that this complement and this negation, these are the same, these are the equivalent words. Okay, so when I say complement, you can think it like negation. Okay, so p and q negation, so whole negation, that will be p dash plus q dash. Similarly there is a second formula for De Morgan formula, that is p or q whole negation. What will be this will be p dash and q dash. So okay, basically what we are doing in De Morgan formula is that we are changing and to or. You can see that there was and here, we changed it to or. You can see there was or here and we changed it to and. Okay, and also what we are doing, we are complementing these these propositional variable. We had p here, q here, so we are getting p dash here, q dash here. Okay, similarly we had p here, q here, we are getting p dash here, q dash here. Okay, so so this is the De Morgan formula. Okay, actually I have written this formula further in the next slides. Okay, but I have explained it here also. Okay, how to prove this, how to prove this? So you can easily prove this using truth table. Basically what you can do, you can make the truth table for this, and you can make the truth table for this, and you can see that the truth values for this is always same as truth values for this. Okay, so similarly you can prove this. Okay, so easily we can prove this De Morgan formula using truth table. Okay, so now what were we seeing? Okay, so NAND operator. So basically NAND operator is nothing not of AND. Okay, so this will be this. Okay, so basically NAND operator is nothing but p dash plus q dash. Or NOR operator, similarly NOR operator is nothing but first what we do, first we OR them. Okay, then we negate them. Okay, first we OR them, then we negate them. Okay, so what will become? So it will become p dash. So basically this thing, first we OR them, then we negate them, then what will we get? We will get p dash and q dash. Okay, so that is what I have written here. So so these are two more operators. Okay, these are not as important as other 6 operators that we have seen. Okay, so far we have seen 8 operators. Okay, negation, conjunction, disjunction, then implication, then exclusive or, then we have seen biconditional, and this NAND and NOR operator. So we have seen all these operators. Okay, today's class was all about actually these operators. Okay, they are very important in mathematical logic, so that's why we have spent this much time. Okay, and we will before the next class we will solve many questions. Okay, on WhatsApp group I will be sending practice questions and solutions for those questions. So basically we will be solving many questions on this whatever we have whatever we have learned so far, and then so that in the next class we can we do not need to spend this much time on other we can easily go through the other topics. Okay, now this is next question. That is what is this next question? Let's solve this. How many rows should a truth table have for a statement involving and different propositions? Okay, you if you remember the truth table for negation, if you remember the truth table for negation, that was this. Okay, if we have p and then we have p dash, if this is 0 1, remember that I sometimes what I do, sometimes I write 1 instead of true and 0 instead of false. Okay, so this also. Okay, so basically if I write 0, then that means false, and if I write 1, that means true. Okay, so we have already seen that if p is 0, then p dash is 1. If p is 1, then p dash is 0. So this is the truth table for negation, we have already seen. So basically if we have this just one propositional variable, then we are getting two rows. Okay, you can see that then we are getting 2 rows, right? If we have already seen the truth table for all other binary operators, for example conjunction, okay, etc, conjunction, disjunction, etc. So we know that there are 4 rows in this truth table. So basically okay, so we have if we have 2 variables, then we are getting 4 rows. Okay, similarly what, okay, if there are n variables, for example let's assume there are n variables, a1, a2 and so on, an. Okay, if we have n variables, then how many rows we will get? We will get, for example we know that we can either assign it 0 or 1. We can so there are 2 possibility for every variable. Okay, every variable can either be 0 or 1. Okay, similarly this a2 either can be 0 or 1. So for every variable there are 2 possibilities. Okay, we can either use 0 or 1. Okay, similarly for all these variables. So basically for every variable we are having 2 possibilities. Okay, for a1 we are having 2 possibilities. So okay, and for a2 also we are having 2 possibilities, and so on. For an also we are having 2 possibilities. So total will be 2 power n possibilities. Okay, so if we just multiply them, then there are, since there are n variables, so we will get 2 power n. So basically in the truth table how many rows we will get? We will get 2 power n. Okay, you can see here, for example, here n was 1, so we will get, we got 2 power 1. Similarly, here n was 2, so we got 2 power 2. So if there are n variables in the formula, then in the truth table we will have 2 power n rows. Okay, so this okay, now I've written this solution here. Okay, you can just go through this solution. I will be uploading these slides. Okay, so okay, I think the time is over. Okay, we have only we have 3 minutes remaining. Let's see this thing. Okay, so these things I've already covered, that's why actually we can just go on. Basically this question is okay, if to write about how can we write a truth table for this statement. For example, if we have this formula, then how can we write a truth table? Okay, you can see that there are only two propositions here, p q. Okay, there are only two propositional variable here. There is p, there is q. So in the truth table we will have 4 rows. We have already seen this thing in the previous question, in the previous exercise. So we will have 4 rows. So basically in the truth table, what will basically in the truth table what we do, we make all the rows for all basically these propositional variables. So here we have only 2 variables, so we got 4 rows. Now okay, since we need to make truth table for this complete thing, then what we can just if you are expert, then you can directly write this truth table here. Okay, you can just directly, you do not need to write these 3 rows or these 3 columns. Okay, but since if you are in the beginning, then what you can do, you can just divide this into parts. For example, you can write a truth table for p and q, which is here. Okay, you can write truth table for p and q, which is here. Similarly, you can write a truth table for not q, and similarly you can write truth table for this. Now finally finally we have implication operator between these two things. Okay, between basically this column and this column. So we already know that implication is always true except in one case. What is that case? That case is this: when this is true, this is false. So basically you can see okay, also this, you can see that this is true, this is false. So when this left hand side of implication operator is true and right hand side of implication operator is false, in this case we get false. Okay, in all other cases we get true. Okay, so you got this truth table. Okay, so this is the way how you can make truth tables for formulas. Okay, so this is a very easy thing. Okay, so now okay, there is just okay, just this last thing we will do, and then we will finish today's lecture. So basically there is for example, if I write this, assume that if I write this p not and q, then what does it mean? Okay, what does it mean? Okay, so if I write this, then okay, I give you two options. Okay, either it could be like this, not p and q. Okay, or it can be like this, not of p and q. Okay, so basically when I write like this, okay, then either this is equivalent to this or this is equivalent to this. Okay, so how can you say? So basically actually what we are doing basically here, this negation operation has higher priority than this AND operation. So this is so this is false, because what does this mean? This means that we are we are giving high priority to AND operation. Okay, here what we are doing, we are giving high priority to negation operation. So basically this is true. So there is this convention, this is there is this convention that we give high precedence to, we give precedence in this order. So the highest precedence is for negation operator, and then we have at second number we have this AND operation. So basically this AND operation, this conjunction operation has higher precedence, higher priority than this disjunction operation or OR operation. Similarly this implication operation has fourth number of priority, and this double implication has a fifth number of priority. So this is the order of precedence. So basically, for example, when I write this, okay, not p and q, then it means that I am basically
I will first do this not P. Okay, I will first do this not P because this negation has high priority, and then then we will compute this conjunction. Okay, so for example here, if I have this P and Q or R, we already know that the conjunction operator has higher precedence than or operator. Okay, so so basically what we will do, so first we will compute this and operation, then we will compute or operation. Similarly here, okay, here again we have or operator and operator, and we already know from this table that and operator has more precedence than this or operator. So first we will compute this. Okay, first we will compute this. You can see that first we will compute this, and then we will compute or. Okay, so so this is the precedence of logical operators. Okay, this is a conventional thing actually. For example, in the exam they can give you they can explicitly give you different precedence. Okay, they can mention that for example, disjunction has higher precedence than and operation. In that case, what you have to do, for example, if I explicitly mention that disjunction operation has more precedence than conjunction operation, then what will happen? Then this thing will be written as P or Q. Then what will happen? Basically, we will compute disjunction operation first, and then we will compute conjunction operation. So basically, this is the concept of precedence. Okay, we already know this concept of precedence in our C programming. Okay, so in programming also you can you already might have studied this precedence, this kind of thing, priority kind of thing. Okay, so so by default this is the precedence. Okay, so time is over. Okay, we are so let's complete today's lecture. Okay, so so we have seen all these things, and again today I will send some practice question on this WhatsApp, and you can solve them. And if you have any doubt, what you need to do, just revise what I have taught in today's lecture, and then you can ask me any doubt on WhatsApp group. Okay, and we will solve many questions today. I will send you around 20 or 30 practice questions. Okay, so okay then we will just pause this recording and you can leave. Okay, bye. See you in the next lecture.